Hi, this is Professor Fernandez, and we are going to work on Module 2 in Lesson 1. So in this module, I want to focus on helping you plot basic shapes in 3D, and we're going to focus specifically on spheres, cylinders, and generalized cylinders. So the first thing I want to talk about is plotting spheres in 3D. So to get to this definition down here of the actual equation of a sphere in 3D, let me first remind you how we plot circles in 2D. So the equation of a circle in 2D, you might know in standard form, is x minus a squared plus y minus b squared equals r squared. And this is the equation that we can very easily read off the center from and also the radius of the circle, r. And if you want to plot this in the plane, this is one of the reasons why we want to get it into this form to begin with, so we can easily spot the center. Let's just assume that a and b are both positive. Then there would be the center, and then the radius r, might look something like this. So there we go. That's a simple plot of a circle. One thing we could do is we could say, okay, since we're going to plot points in 3D and we're thinking about, heading toward plotting spheres, maybe we can start with this left-hand side and maybe we can just add a z minus c squared, right? So what am I doing? I'm continuing the pattern from the first video that, a three-dimensional space R3 is just add another z, add a z component to your point to make it from a point x comma y to a point x, y, z. And then I'm here just following the pattern of a, b, and c. And then I'll keep the right-hand side the same to maintain the interpretation of the set of points the same distance, equidistant from some center. So that's essentially the definition that we get down here. So that's the standard form of the equation of a sphere in 3 dimensions. So the equation of a sphere of radius r centered at the point ABC in R3 is x minus a squared plus y minus b squared plus z minus c squared equals r squared. So this should seem like a nice general extension of the equation of a circle. I mean, if I go here and just kind of blot out this part, right, then we get the equation of a circle. So that should make sense. If I draw a sphere, here's my depiction of a sphere. It really does look like a collection of circles, almost, in whatever orientation or direction you want to look at it as, right? So there are 2 circles within this sphere. Here's another circle that goes around this way, right? And we could just keep doing this forever. So that's another way to think about why you should expect that mathematically the equation of a circle would be inside the equation of a sphere, because certainly visually that's what's going on. So what I want to do now is help to make this connection even more explicit by talking about the other view, which I alluded to earlier, of what a circle is, the view of a set of points equidistant from a center. So if we look at this equation for the sphere, and again, we go back to the equation for a circle to help us to where we're going next, right? This is the set of points, a distance r from AB, right? That's exactly what this picture says. That's how we think of a circle. All the points that are the same distance from another point, and we call those we call that common distance the radius of the circle. So one way we could think about this and connect it to something you might already know is the Pythagorean distance. So if we take the square root of both sides, remembering that r is a radius, so it's not a negative quantity, right? Then really this is a different view on what the equation of a circle is telling us. If we go back to our AB here, here's the point AB, and let's say the radius is r, then you might, squint and look at the left-hand side and think about the Pythagorean theorem. Why? Because if this is the point out here, which is x comma y, which is, we're saying is on the circle, then if I kind of extract, what's going on here, I have this point here, which is AB, and then I have this other point here, which is xy. And then the horizontal extent, right? This triangle here is x minus a. And then the vertical extent, this part here, is y minus b. And it's a right triangle. So thinking back to geometry, since this is r, well, the hypotenuse here is just Pythagorean theorem, right? R squared is the side length x minus a squared plus the the vertical side length y minus b squared. That is the equation of a circle, right? So, this is something, again, you probably already know, that we can see triangles embedded in the circle, right? So here's a little right triangle specifically. And this leads, of course, to trigonometry and sine, cosine, and tangent. For my purposes here, I want to use this as a motivation to point out, again, that the equation of the circle can be reinterpreted by just basically taking a square root as either coming from or giving rise to the notion of a distance between 2 points in the plane. So in very similar fashion, the equation of a sphere can be thought of as coming from or giving rise to, wherever you want to start, the notion of a distance between 2 points, this time in R3. So that leads to this theorem. It is a theorem because this is something that has a proof, and the proof actually uses the Pythagorean theorem, a few times. So this is something that I invite you to prove in the practice problems, and I kind of walk you through it. But the Euclidean distance in R3 is defined as follows. So suppose we have 2 points x, y, z, and a point a, b, c. Then the Euclidean distance, I'll tell you about this notation in a minute, is basically the Pythagorean theorem in 3 dimensions. So again, if you blot out this part, that would be the distance that we just talked about over here between 2 points in the plane. So what we're doing down here is we're basically extending this result to R3. So if I think of R3 and I have a point over here and another point over there, again, it's a little hard to draw this, but the distance of the line segment PQ connecting these 2 points, which is now this notation, these vertical bars will come to signify a lot more later on when we talk about vectors. For now, I would encourage you to think about this thing as one quantity, the distance of the line segment PQ. Later on, we'll talk about these vertical bars as a norm, but that'll have a different context attached to it. So anyway, so the distance of the line segments here between P and Q, we are thinking about as a Pythagorean distance. P has 3 components, Q has 3 components. So what this new distance formula is doing is just the same thing the old distance formula was doing. It's finding what is the change in x components, and then it squares it. What is the change in y components? Squares it. What's the change in z components? Squares it. And then it adds those up and takes the square root. So that's the natural extension of this formula up here, the Pythagorean distance between 2 points in the plane, to the Euclidean distance between 2 points in R3. So what I want to do now is connect these two things in a visual way for you. So now we have this equation of a sphere. We have a distance notion of 2 points in the plane. Excuse me. So the first way that I'll connect this is, again, going back to what I alluded to a few minutes ago. So when you think about a sphere, right, just like a circle is the set of points in the plane, equidistant from a center, a sphere is the set of points in R3, equidistant from a center. And now we know what that means. We have this notion of Euclidean distance. So if I go back to this notion of the points PQ, the line segment distance, being the square root of these sums of squares, I can then say, okay, great. What if I look at the set of x, y, z such that the square root of x minus a squared plus y minus b squared plus z minus c squared equals the same number r? Well, then if I square both sides here, that gets me back to the formula for the equation of a sphere. So again, what we're seeing is that you can go both ways. The way I've presented it is that the equation of a sphere algebraically follows naturally from the standard form of the equation of a circle. You just add the z minus c squared term. But you could also go this way that I've just presented it. If you look at the set of points in R3, whose distance from a point A, B, C is the same distance, r, and then you square that relation, you get back to the same place, the equation of a sphere. So two different ways to think about what a sphere is and how it relates to Euclidean distance. Okay, so now let's move on to some examples. Here's example 1.2. Consider the equation x squared plus 2x plus y squared minus 4y plus z squared equals 4. So I say here this equation is the equation of a sphere in disguise. Find the sphere's center and radius. So let's do that first, and then we'll come back to number 2. Okay, so number 1 here is, well, what are we being asked to do? We're going to find the sphere's center and radius. To do that, we want to put the equation in the standard form that we talked about earlier. And to do that, we might have to complete the square sometime, so I'll remind you how that goes. So the first part here, I have x squared plus 2x. To complete this square, I want to add half of this number, and then square it, and then subtract the same thing. And then I also have this part up here, so I have plus y squared minus 4y. I'll do the same thing there. I want to add half of this number, squared, and then subtract the same thing. And then I have a plus z squared over here. There's nothing that I want to do with that. That's already a perfect square. And then I have equals 4. Great, so then let me combine things to make our perfect squares. So what I do now is I combine the x, I keep the sign with whatever the number here is. So 2 over 2 is 1. So I get x plus 1. That's my perfect square. Okay. And then you're always going to keep this positive number inside that pops out of when you square this out. And then you'll have left over whatever this number is. So I have a minus 1. And as a quick check, right, we want to do this out. This is x squared plus 2x plus 1 minus 1. Those would cancel, getting us back to where we started from, x squared plus 2x. Great. So we have successfully completed the square for the x portion of this equation. Let's do the same thing now for the y portion. So we'll do the similar thing here. We will do this, keep the sign, and then put in this number. 4 over 2 is 2. So now when we double check here, we square this, we would get y squared minus 4y plus 4, right? And then this is a number that will tag along for the ride. This is 2 squared, so minus 4. Minus 4. And then again, that gets us back to y squared minus 4y, which we started from. So, you know, I won't do this every time. Actually, this is the last time I'll do it. I'm just, again, reviewing, completing the square, and making sure that you're comfortable with how to check your work for when you do complete the square in one of these types of example problems. So we get here, and then we're almost to the point where we can identify the center and the radius. So what I'm going to do is move all the numbers to the right hand side. So I'm going to add 4, I'm going to add 1, that's 5, plus 4 gives us 9. Okay, so you might be able to see here the center and the radius. I'm going to scroll up really quick to remind you how to read these off. So let's clear some things here. So the center you read off from x minus a, y minus b, z minus c, and the center is abc. And then the radius, you take the square root of whatever number is there. So let's take a look at that. So this here is x plus 1. We could also view that as x minus negative 1. So negative 1 is the x component of the center of this sphere. This is already in y minus b form, so the b here is 2. And this can be viewed as z minus 0. So the z component is 0. So that's the center of our sphere. And then the radius, we take the square root of this number, remembering that the radius is a positive number. So that's 3. Great. Great, so we have found the center and the radius of the sphere. So I'm going to go back and see what other things I suggested we work on. And then a question, how far from the origin is the center of the sphere? Okay, so the center of the sphere, how far is that from the origin? Great, so let's talk first about the center. So we just found that the center of the sphere, minus 1, 2, 0. And the origin is the point 0, 0, 0. So now we're being asked about the distance between 2 points in R3. So we are going to go back and use our distance formula. So let's call this point P. Let's call this point Q. So we are being asked to think about the distance of the line segment connecting points P and Q. And we know based on our formula, which is, just again, the square root of the sphere formula basically, that it's the change in x values squared plus the change in y values squared plus the change in z values squared. So let's see what happens here. So I get negative 1 squared plus 2 squared plus 0 squared. So I get 1 plus 4 plus 0. I get square root of 5. So that's how far the center of the sphere is from the origin in terms of its Euclidean distance. You might be wondering why I keep talking about Euclidean distance. Why don't I just say distance? And I actually will for pretty much the rest of the course after I make this comment, which is that there are different ways to measure distance in R3 and in other spaces. You might, for example, if you've ever taken a taxi, taxis measure distance differently. So they don't charge you based on the Euclidean distance between your starting point and your destination. They charge you based on either how far the taxi travels or how much time it takes for you to be in the ride. But those two are almost never the same as a Euclidean distance because most cities are laid out in a grid. So you have to do lots of forward, left, right, back type of movements that are not just the shortest distance between 2 points A and B. To do that, you might have to run through a tree or something, and obviously the taxi's not going to do that. So because there are different ways to measure distance in spaces, including R3, we try to pick a particular type of way of measuring distance and then build the rest of whatever we're going to do in the space around that. For this course, that particular way of measuring distance is the Euclidean distance. That being said, because that's not going to change from here on out in other videos, when I say distance between 2 points in R3, I will mean the Euclidean distance. So I'll stop referring to that qualifier Euclidean. Okay, so one thing I wanted to do before I move on, and I say this a little bit up here. So I'm going to look at this applet and show you what the sphere that we obtained over here looks like, right? So we can go into R3, we can start here and then draw the set of points that are a distance 3 away from this center. That set is going to be a sphere. The surface of the sphere is a set of those points. So let me show you what that looks like. We'll see if, you can see it on the corner there. Oh, great, it's still there. So you see in the upper left here, this is the A point, that is the center. The way this particular applet works, you have to put in a B point so that it knows essentially what the radius of the sphere is by calculating the distance between A and B. So what I did basically is I took the z component of 0 and I just added 3, right? So that point is a distance 3 away from point A. And then it plots the sphere as this red blob. So you can pan around here and just to double check things. If I pan around a little bit here, our point A has a negative, so the x-axis here is red and the y-axis is green. Our point A, you can see there in the toward the center of the screen, has x-coordinate -1, y-coordinate 2, and then the z-axis is blue. So you can see that A's z component is 0, so it's on the xy plane. And then the radius is 3, so you can see that B is at a distance 3 above the plane, And what the applet is doing now is it's drawing the set of all points a distance 3 from A. You can see that, the right most extent of the sphere, because, let's do it this way, because the x-coordinate is -1, if we go 3 units to the right, we get to x equals 2. So you can see that that's the rightmost extent of the sphere at x equals 2. If we go 3 units to the left of -1, we get to -4. That's the leftmost extent. So, by playing around with this, you can get a better sense of what spheres look like and just, pan around and see how changing the x, y, z components changes where the sphere is and how big the sphere is. I'm going to try here to maybe tap, right? And we can change, and you can see in the left-hand side how this changes a lot about the sphere. Notice that because of the way I put in the sphere, the z component of b is telling us basically the radius of the sphere. So there I am going back to 3, and you see the equation of the sphere has a 9 on the right-hand side, 3 squared. As I decrease this, and maybe let's try to go to 2, the right-hand side is 2 squared, which is 4. So this is just one way to get a sense of, what changing the radius does to the sphere. We can also change the center. So I can move the sphere around. Because I'm changing the center, right? The interpretation of what's happening here is a little different, because for some reason the applet has ignored the z component, or I guess there is a z component, but as you pan around, it's changing some of that. So I encourage you to play around with this applet to get a better sense of how changing different components, different aspects of the formula of the equation of a sphere changes what the sphere looks like. Great, so let's go back to the rest of the lesson. So we've learned how to plot spheres, we've learned about Euclidean distance, and we've learned about how it all relates to and interacts with the equation of a circle. Generalizes naturally from that. So now let's talk next about generalized cylinders. So you might be wondering, what are we talking here about generalized cylinders? Okay, so let me give you a little bit of a motivation. So I'm going to erase this. So, so we have more space to think. So let's talk first about the simpler notion of, going back to circles, the shape that the unit circle makes. And let's think about it in R2 and then in R3. All right. So let's first talk about x squared plus y squared equals 1. So we're familiar with this. This is the unit circle centered at the origin. There we go, 1, 0. Radius 1. So let's ask the question. Interesting question. What shape does x squared plus y squared equals 1 generate in R3? Interesting question, because you might be tempted to say a circle, right? It's a circle. Why would it be anything else in R3? But I wouldn't go, to that sort of natural answer right away. Remember that R3 is a set of points x, y, z. This is what we talked about in the first module, such that x, y, z are real numbers. In other words, R3 has a z component. The points in R3 have a z component. So if I am trying to figure out what the circle x squared plus y squared equals 1 looks like or generates in R3 as a set of points, I have to think about the z component. And when we're talking about it that way, we realize that there is no z component that's specified in this equation. So we could pick whatever z component we want. So that gives you a little bit of a clue as to what's going to happen. So if I go back and I draw my axes here, x, y, z, and I then redraw my circle in the xy plane, which now looks like this, right? Here's my point 1, 0, 0. Well, I could just as easily draw the same circle at z equals 1, right? There's absolutely no rule against doing this because x squared plus y squared equals 1 doesn't have a z component. Z is left unspecified. So z can be whatever you want. I can also draw my circle down here as z equals -1. And it'll be the exact same looking circle. And you can see now that I can just keep doing this. For any z value, I pick the z value and I look at the plane defined by that z value and I just draw the unit circle on that plane. So the shape that we get is a cylinder. So that's the answer. What does this x squared plus y squared equals 1 look like? In R3, it is a cylinder. And it's a very specific cylinder. It has a very specific orientation, very specific size, if you will. So to recap, in R2, x squared plus y squared equals 1 yields a circle, the unit circle we're familiar with. In R3, because z is left unspecified, z can be whatever you want. And so plotting x squared plus y squared equals 1 for every z equals whatever number you want plane yields a cylinder. Okay, so this is one of the cool / wacky things about moving from R2 to R3. This is why I wanted to start with the equation of the sphere as generalization as the equation of a circle, because that move is a little more familiar and not as seemingly wacky or strange as what's happening here. But so the point is that you can now extend this, so what if we weren't drawing x squared plus y squared equals 1 in R3? What if we wanted to draw x squared plus z squared equals 1? We think that would also generate a cylinder, but it might be in a different orientation. Or maybe y squared plus z squared equals 1. That one leaves x unspecified. So maybe it generates a cylinder, but also in a different orientation. So this leads to the notion of a generalized cylinder and of this idea of rulings. So here's a definition for generalized cylinders. By the way, every once in a while I will refer to this page number, and this is the page number corresponding to information in the textbook for the course, which is Apex Calculus. I'm just going to scroll down really quick to show you where you can find the link. So here it is. If you click on this button, you will be taken to the book. This book is open source, so you can download it for free. It has embedded 3D graphics, so you can pan around using the PDF file. It's really phenomenally well done for it being free, and is a really great way to learn the content of the course and have a resource for it beyond these notes. So let me go back to where we were. So what does this theorem say? The theorem says, let C be a curve in a plane, and let L be a line not parallel to C. Okay. So let's draw what's going on here. So C is a curve in the plane. And we're going to think of this as a closed curve. And then L is going to be a line not parallel to C. So what do we mean by that? Well, so parallel to C. So we're talking here about trying to think in 3D. So we're thinking in terms of, for now, let's think of the plane xy. We're thinking of the curve in the plane xy. And when we're talking about lines, right, we are thinking about a line that is perpendicular to the curve. So there's some, and this is the way the definition is phrased in the textbook, there's some what I would call not hidden, but there's a little bit more to what is said in the definition. So what we have in mind is a curve C, and we have these lines that kind of touch the curve, but not in the same plane as the curve. So a generalized cylinder is a set of all lines parallel to L that pass through C. So I've drawn one such line here, and I'm going to draw another one that touches C here, and I'll draw another one that touches C there, draw another one that touches C there, and now you can get a sense of what a generalized cylinder is. If I kept doing this, I would obtain, here's this wacky curve. I'm going to try to draw it again over here. I would obtain something that kind of looks like a cylinder. If I connected these and then the ones in the back here, down there. right? And then I would just kind of fill this in with all the ones from the front and all the ones from the back. So you can see that is why it's called a generalized cylinder. It's not exactly a cylinder. There aren't circles, but it looks like a cylinder, kind of, mashed or moved around or manipulated. So the curve C is called the directrix of the cylinder, and the lines are called the rulings. Okay, so what I've done here really is already specialize this definition to the only case that we're going to talk about in this course, which is when the rulings of the generalized cylinders are perpendicular to the plane containing the curve C. Right, so that's how I've explained it exactly in this diagram and what I've drawn. As the definition implies, things can get more general. The rulings don't have to be perpendicular. You might draw something and the rulings might do this. They might slant a little bit. So you might get this cylinder with a slant. But that algebraically is a little more complicated than what we want to do for the course. So I'm just really after generalizing the cylinder shape that we started with when we were thinking about the unit circle. So that being said, let me erase all this and talk about this example so we can get a sense for how this works in practice. Okay, so this example says, plot the following curves as generalized cylinders and identify the directrix in each case. Remember, the directrix is the curve C, which for us is going to be in the plane. Okay, so let's talk about y equals x squared first. So y equals x squared, x, y. If we draw it in the plane, a familiar parabola, there it is. And if we now think of this as a generalized cylinder in R3, well, we're going to draw our parabola in R3, y equals x squared, goes back there, goes like this. Great, in the plane. And then we are going to find, we're going to draw rulings perpendicular to the plane containing the curve C. So the plane containing the curve C in this case is the xy plane. The curve C is the parabola, and therefore that is our directrix. So this is our directrix. Okay, so we've identified the directrix. And then we're going to plot the generalized cylinder that we obtained from here. So what do? We take, as I've been saying, I will only ask in this course about rulings perpendicular to the plane containing the curve. So that's perpendicular to the xy plane. So these are the rulings. Okay. So what do I obtain? I obtain, if I redraw the parabola up here, and maybe I redraw portions of it back here. So what do I get? I get this shape that kind of continues going on, and it's kind of like a parabolic sheet. So, it reminds me of one of these aluminum sheets or even a piece of paper. If you take a piece of paper and you fold it in the shape of a parabola, then you will be getting something similar to what this generalized cylinder looks like. Of course, it extends infinitely in the up and down directions, positive and negative z-axis. And then also it just keeps going that way and it keeps going this way because y equals x squared just goes on and on. So that's a rough idea of what this generalized cylinder looks like. Let's go back to number 2. Z equals cosine of y. So first thing I'm going to do is I'm going to plot z against y. So cosine of y. So quick little review of trig, right? Cosine of 0 is 1. And then we have cosine of pi over 2, which is 0. And we have cosine of pi, which is negative 1. That's down here. And then the cosine graph just kind of keeps going from there and oscillates. Okay, so that's our cosine graph. So this is z in terms of y. So I haven't specified x. So once I translate this to the x, y, z plane, here is my cosine graph in the z, y plane. And now I haven't specified x. So the rulings here are perpendicular to the plane containing the curve. So the curve in this case is z equals cosine y. That's our directrix. The plane is zy. So the rulings are perpendicular to that plane, which is in the x direction. So I'm going to do basically the same thing I did before, and I'm going to plot this curve again over here, and then I'm going to draw rulings that are parallel to the x-axis, right? And this one is even harder to draw than the one before, but you can kind of hopefully get a sense of what this generalized cylinder looks like, right? So you have this wavy sheet that continues to wave, and has these rulings that are parallel to the x-axis, and of course it goes off in both directions infinitely far. So that is the generalized cylinder that we obtain. Okay, great. So a quick little recap of this last concept for this module. Generalized cylinders, although they can be more general, for us in this course, we will take, I will only ask you about generalized cylinders in which the rulings are perpendicular to the plane containing the curve C. So you will only ever see those types of questions and practice problems in the examples, for example. Great. So like I said, the textbook, the Apex Calculus textbook, has a lot of embedded 3D graphics. I highly encourage you to check them out. In particular, these two figures are really nice ones to see some of this generalized cylinders in action, and you can rotate and move around with them. And the last thing I want to say about this lesson is that there's so much more to say about plotting in 3D, but we'll return to all of that in due time in subsequent lessons. In the next lesson, we're going to shift gears a little bit and return to the structure of R3 to look at that space a little differently. Rather than looking at it as a space of points, which is most of what we've done here, we are going to look at it as a space of directions. So that's going to lead us to the notion of vectors, which is going to come in really handy for the rest of the course. This page is a page of suggested practice problems. I have a note up here. If you're going to be solving these, you don't have to solve all of them. They really are meant for practice. So some of these, when a section is mentioned, is coming from the section in the Apex Calculus book. Other times I might add additional problems. If there is a boldface information that precedes the problem, that is really kind of a mathematical extension or application or maybe a proof for something. In this case, this is what I had promised, proving the Euclidean distance formula, and there is sort of a nice little diagram from Wikipedia that is going to help you do this proof. Sometimes there might be something like this, but in blue text, and that is an application of some of the ideas or concepts in the lesson, real-world application. So that's it for this lesson, and I will see you in the next one.